I'm not sure why she can't view the stream, but I can share the link to the lecture. Anyway, there was, to talk about what we're going to do today, first, there was some petition from UNC for people to work on coronavirus-related AR/VR apps. Specifically, they said that they want some people to work on innovative ways of doing practitioner training and improving task performance and things like that. We happen to already be working on that in Henry Fuchs's group. So if anybody's interested in that, you can let me know. I'm figuring out if there's any kind of conflict of interest if somebody wanted to do that as a final project. I think if you were to do that, we might just have to have a third party be a part of choosing your final grade. So I don't think it would be that big of a deal. So let me know if you're interested in doing this as a final project or just in general. I'm putting assignment 8 up later tonight, and I did finally put up the Steam Audio demo lecture. For assignment 8, the VR part is not super important unless you already have a VR headset that you're using, which is only a few of you. So if your current VR implementation is really bad or you're just not happy with it, you can start from assignment 4 instead. The VR character is not really necessary to get the audio working, and if you want, you can just use the first-person character, like Unreal's first-person character or first-person all-in-one in Unity. You will need to build the projects for whatever platform you're using and share it with a couple of people. You'll have 2 people do your treasure hunt without spatial audio and 2 that do it with. The dependent variable is really simple this time. You're just going to measure how much time it takes them to actually find it, to find the 10 collectibles. So you know there aren't really that many intermediate steps in calculating the dependent variables this time around. If you share the project with other people, you could just have them time themselves. It's fine if it's a relatively rough estimate. For extra credit, you'll have a third group that does the same task with propagation. So in this case, you'll have a 3-group ANOVA. The midterm assignment is due tonight. A lot of people have already submitted it. You can't use late days on it at all, and it shouldn't take that long, but still don't start at the last minute. I mean, if you were looking for a really easy way to erase 10% of your grade, here it is, submitting it late, so don't do that. Unless I provided you with some exception, you should not submit it late. I mean, it's as simple as that. And then we'll talk about 3D animation. And today we'll talk about 2 of the most important methods for VR, which are Blendshapes and skeletal animation. If today's your birthday, too bad. Get wrecked. So recall that our goal is to meet the parameters for a good avatar. In this paper, they describe a good avatar as one that has accurate visuals from your perspective, audio is spatialized and sounds good, and the movement is good, as in the physical body gestures are as one-to-one as they need to be for your application, and so on. So with animation, we try to, we're appealing to both the visuals and the movement. We haven't really gotten to movement yet because we're still doing relatively basic animation without inverse kinematics, so for now we're worrying about visuals. Last time we talked about what makes the newer VR games that are so popular so different from older ones. There's some fundamental difference, such as in some of these games your entire body is represented, and this is done with skeletal rigging and IK, which we'll talk about probably on Wednesday. And there is also the addition of physical interaction with objects in the virtual environment, which older VR games didn't really have, at least not to this detail. Is somebody asking a question? No, just mute yourself then. And some of this is done with inverse kinematics. So, for example, if you want to have somebody be able to be shot in the arm specifically, you won't know where their arm is with just the VR tracking, but you can easily figure it out with IK. So that's what these games are doing. Our ultimate goal is to understand IK, and in order to do that, we need to understand other animation methods. I'm just going to skim through these slides because they're basically review. And we talked about what actually is 3D animation. it's essentially anything that would cause a mesh to not be static. So the meshes that you've been using, like primitives, like these rectangular prisms, are completely static. They always look the same, even if they're in different positions in the virtual environment. We want meshes that can actually do things besides just be there. So they have some kind of motion. In some cases, the motions are totally predefined, like the jump animation here, and this is a cycle. Some of the motions are more complicated, and they require us to describe them with graphs. So if you want to describe, crouching, walking, running, sprinting, and so on, you'll need a state machine to smoothly transition between those things. So for example, if you wanted your character to jump, you would need them to go upwards first, then they'll be idle in the air for a second, and then they will fall down. So you need a state machine to describe a smooth transition like that. And some motions are physics constrained, so ragdoll, IK, and so on. And we use animation to describe any of these methods. Last time we talked about geometry caches and simple transforms. Today we'll talk about higher order transforms, Blendshapes, and skeletons. And on Wednesday we'll talk about IK. So just to review geometry caches, a geometry cache is the closest equivalent to how a lot of 2D animation is done, as in they're just pictures that you scroll through, for example, sprites. So the Mario animation is done by just scrolling between these images. And in geometry caches, you do basically the same thing. You save a mesh for each frame, and then you transition between those at a certain frame rate. And there will be some single file that describes, each part of the animation, the same way that in 2D we have videos that do this for us, like MP4s and GIFs or GIFs, whichever party you're part of, and so on. In 3D, we have files like Alembic. There are some pros of this method, such as you can represent any arbitrary animation. They're very easy to understand at a high level, and for animations that are way too complicated to describe with other methods, this is a good last resort. So physics animations especially. And in movies, they're used to describe very detailed animations like the Graham-Tarkin animation. Some cons: they're pretty slow, and part of this is that meshes are much bigger than a single frame of video, so it's just there's a lot of hardware that needs to be strong. Like you would want an SSD, you would want to be able to read from the SSD quickly and process the data quickly in the game engine, so there's some CPU or GPU limitation depending on how you do it. And they're also very resource intensive, even outside of the context of loading the frames. Assume that you can load all the frames at once, they're just very resource intensive. So in the telepresence group, we were doing this animation where this grad student in our group was giving a tour of Sitterson, and it's a pretty simple animation, and it seems like it wouldn't require that much data, but it required like 80 gigs of disk space and 40 gigs of RAM. So, and this is only a 1-minute animation where each mesh is 20 megabytes, which is definitely high for a mesh, but even so, you could imagine that there is a lot of memory overhead. Game engines don't support geometry caches well, at least they didn't for a very long time. Even nowadays, I think Alembic is one of the only file formats for geometry caches that is actually supported. And usually we only use this method for really, really impossible animations. So obviously these aren't great for real-time game engines. Nowadays we use any keyframe-based method. Whenever I show videos, it stops being full screen, which is annoying. Nowadays we stick to keyframe-based methods, and we interpolate so that we can figure out where a mesh is at certain point. Well, we can define where a mesh would be or in what pose it would be at certain points, and then we can interpolate to save data and just predict where it will be at any other points. So keyframes, for a very simple transformation, keyframes are just frames that you define as causing some sudden transformation change. So in this case, the 0th keyframe describes the cube being over here, and maybe the 20th keyframe describes it being way over here, and you interpolate between these two. so that you don't have to do a geometry cache style where you save a cube, an entire cube for each frame of this 20 animation, for example, or 20 frame sequence, because that would be really slow and unnecessary. We can interpolate smoothly between the keyframes, so we can do it linearly. In this case, it's probably linear because there's a one-for-one correspondence between the cube moving and the timeline moving. In some cases, you might use sinusoidal functions, in which case the mesh would animate very slowly in the beginning, and then it will speed up, and then it will move slowly again. Last time I showed a Blender example, which I think was this one, where you're transforming the monkey head. So on the 0th frame, it's here, and then I described changes in location, rotation, and scale. And if you move between the keyframes, you'll see that it does this. I have it rotate, it scales up, and it moves. And if I want to move it back, all I did was copy this set of keys onto slide or frame 60 so that it would go back. So simple transformations are, they're simple. I don't think it's very hard to understand keyframes. For any higher order trajectory, so here we are only describing linear changes in rotation location or rotation. If we want to predefine any higher order trajectory, so if we want the object to move in a curve, for example, we need to use splines, or at least in game engines, it's assumed that we would use a spline. So these are just higher order versions of simple animations that we just looked at. You can apply these as some part of any other animation method. Whenever you have a predefined trajectory that's not linear, we typically use splines. So for example, if you're simulating a camera dolly, you would want to use a spline that will do this. When you want to give the impression of good navigation for things that are predefined, splines will usually help you do that. So for example, in a game when there's a cutscene where, a plane is, or a helicopter is moving through a city, that animation is always the same, so there's no need to do the navigation in real time. We can just predefine it with a spline. So we use splines for things that fly usually, and cameras. And splines are very efficient, as we discussed at some point a few lectures ago, so you can actually recompute them each frame. And if you do that, you can give a more dynamic impression. So here is some example of using splines in Unreal. I will speed it up a little bit. But in this, initially, this guy has a linear trajectory. So the cube would just move left and right. But then he defines another control point, which will cause the cube to move in a curve. Can you mute yourself, please? Whoever is typing. Otherwise, I'll forcibly mute you. Anyway, you can see that this guy, he defined this spline. He just added a few more control points. And typically, splines in game engines are cubic, which means that they are differentiable down to the third derivative, I believe. Which means that down to that derivative, any merge of a bunch of splines will be smooth. It's not important, the details in this case. This is just an example. So, moving on. What we were going to talk about last time that we didn't have time for were blend shapes. Blend shapes are pretty cool, and I can find plenty of funny videos of them in action. But the idea of a blend shape, and blend shapes go by a lot of different names. In Maya and Unreal, I believe they're called morph targets. Blender calls them shape keys. I don't remember what Unity calls them, but blend shape is a pretty standard term to use in research applications, at least. But in any case, these are essentially better optimized. You could think of them as geometry caches almost, where you're only defining the most extreme transformations and interpolating between them. So, for example, well, actually, I'll show you a real-time example in a little bit, but we commonly use blend shapes for facial animation and lip sync. The idea is that there's a basis pose where your face, for example, is in a neutral pose, and you define blend shapes as extreme transformations of each vertex relative to the basis pose. So, for example, she's doing this motion, and the frame where her chin is all the way down might be the basis pose, and the motion is the blend shape is when the chin is all the way up, and you can interpolate between those two. You typically have a scale from 0 to 1 or 100% describing how much of the blend shape you actually use. So, for example, if you're looking at this really excited dude right here, maybe you could think of it as this second face is like, let's say that this first one here is the basis pose. I have a pointer. Let's say that this one is the basis pose, and this is some very extreme transformation. This one here might be like 50% of the way to super hype. So you can use blend shapes and interpolate between them. You can typically combine a bunch of different interpolations towards a blend shape, as we'll see in a second, to allow for more complex animations. So, as a very simple example in Blender, can you see my Blender screen, by the way?
Yeah, I can see just fine.
Great. Say that I have my monkey. You don't have to know exactly how to do this in Blender, but you're free to look at the video again if you want to know. For this monkey, I'm going to make it a little bit more detailed. So for this monkey, let's say that I want this to be the monkey's neutral face. So I'll define this as a basis pose. And now I want to define some other pose. Let's say this is going to be a really, really ugly shocked pose, but let's say that the shocked pose, oh god. Let's say the shocked pose looks like this. I don't know. I'm making up a creature that does this as being shocked. Anyway, that'll be my shocked pose, and this is an extremity, key 1, and let's say shocked. Shocked is an extremity, and I can interpolate towards it to get to that blend shape. And I can have more of them, so let's say that I want another blend shape that describes, I don't know, sniffing. Why not? Let's say that this blend shape will be the nose being, let's say that this creature that I define now, when it sniffs something, its nose goes really close to the thing it's sniffing, like Pinocchio. And, you know, I can interpolate to that blend shape, and you can merge both blend shapes by interpolating both of them, so, or defining some amount of both of them. So apparently my monkey, when it's shocked and it's sniffing something, this is what it does. This is what I'm going to do with the resmesh very soon. So that's a very simple example. We'll see better examples related to human creatures very soon. How do people actually make the blend shapes? I did just show you an example, but how do you make more complicated blend shapes? Usually we do it with a skeleton, and we'll be talking about skeletons very soon. Sometimes you do it manually like I just did, but this is less feasible for really detailed animations. Like if my monkey actually needed to be a realistic animal, obviously I can't just move the vertices all manually. It's too difficult, especially if you have a lot of vertices. Sometimes we do it with tracking. We'll talk much later about markerless tracking, which is a topic in AR. Sometimes you do it with reconstruction with markers. Again, we'll talk about this later. And more recently, people have been using machine learning or computer vision or GANs to figure out what the blend shape weights are. So how much do you interpolate to achieve a certain facial structure. So here's some examples of really detailed animations. Like this one was made in Unreal by it's called Snapper's mocap. Anyway, this is marker-based tracking, but you can see that it's pretty good and the detail is nice. And this is all done with a bunch of blend shapes and possibly some physics. But yeah, they're just they're using the control points to interpolate between some blend shapes. This is an example of, I believe this is from Disney Research, who I believe did this with. I believe this is a form of markerless tracking. I'm not great with tracking, but they're trying to track these patches, so they subsection the face, and they shoot a bunch of infrared lights at it, and they try to figure out what happens to the infrared light as the person moves each frame. And they're trying to figure out how to reconstruct certain facial expressions by tracking the face over time. So he makes this pose, they track the patches, and then they smooth it out a little bit so that it looks more natural. It looks pretty creepy. This is done with markers, so they paint some dots onto the guy's face and they use those as control points, sort of like that other version. Anyway, you can check out this video if you're interested, but the point is that it's, you can make really detailed facial expressions for games this way. They're just tracking various types. And then as a final example, this was another Unreal demo from a long time ago, but this was a really, really detailed face that came out a few years ago, I think. I don't remember if it's real time or not, but they have some camera in front of the guy's face that they're using to track his expressions. So, yeah, you can check out these videos. I think they're pretty cool. Being that it's running in a game engine, I'm assuming it's real time, but I'm not sure off the top of my head. Nowadays, one of the most popular uses of Blendshapes, especially in AR/VR, is lip sync. So the general idea, well, let me first define what lip sync is. If I say something into the microphone, how do I make the virtual character that is describing me, make the facial expression that would appropriately represent what I'm saying? And the reason that we'll see this in a second, but the reason this is important is because if somebody is saying something real time, like let's say that you're in a multiplayer game, you don't know what their animation is beforehand because you don't know what they're going to say. So what we do instead is in real time, we go through some process that I'm about to define, and we create the animations dynamically. So the general idea is you make blend shapes for very extreme facial expressions, so like mouth open, mouth closed. You define phonemes, which in language are they're extremities in possible syllables that you can use to talk. You define phonemes as some linear combination of blend shapes, and you can do a linear combination of phonemes to create graphemes, which are syllables basically. And you could keep going on and on to make words and sentences and so on. So nowadays it's becoming more and more common to just use NLP to figure out what the person's saying. So as I'm talking into this mic, you would use an NLP algorithm to get the actual words, and then from the words you can split it up into syllables. From the syllables you can split it up into phonemes, and from there you can just grab the blend shape interpolation weights and create the lips for each thing that I say. So I'll show you a Unity example in a second, but to describe some of the method, blend shapes can be stored by FBXs. I know that previously we haven't really defined what the difference between an FBX and OBJ is. I just mentioned that they're 3D graphics or 3D modeling formats, but I think I did briefly mention a few times throughout the class that FBXs store animation. In this case, they're storing blend shapes. Unreal and Unity both natively have support for blend shapes nowadays, which is nice. And we'll talk about skeletons soon, but blend shapes and skeletons can work simultaneously on the same mesh. which other methods cannot do. And also, if you, for example, with this guy right here, say that, okay, for this guy, say that I'm using some physics method in Blender to generate the hair on his face, like his facial hair. I also need to generate blend shapes for the hair itself, because the hair around his lips especially will deform a lot. Anyway, I'll show you an example. In Unity, there was this cool plugin called Lip Sync. It's deprecated at this point, but if anybody wants to try it, I can share the Unity package with you. There was a free version called Lip Sync Lite, which we used in the HoloLens for something. But anyway, they have this demo with Abraham Lincoln. I don't think there's any audio being shared right now, but it's not important. He's saying the...
7 years ago, our fathers brought forth on this continent a new nation, conceived in liberty, and dedicated to the proposition that all men are created equal.
They defined it somewhere. I don't remember where they defined the actual audio source, but in any case, Lincoln, in lip sync, you define the phonemes with blend shapes. So this phoneme it's simply an interpolation along the mouth open blend shape. For E, it's more complicated, so they have a few interpolants. You can mess with them if you want. And they define plenty of other blend shapes. This one is just jawed down, I guess. FV, I guess. F and V are two more complicated ones, so he's making the F sound and so on. So it's just a linear combination of blend shapes. The FBX, the blend shapes are defined in the FBX, so Lincoln is FBX, wherever that was. Lincoln's FBX under... I don't remember where the blend shapes are described. They're somewhere over here. Anyway, somewhere in the import settings there are all the blend shapes. But anyway, this is an FBX. So if you do show in Explorer, you'll see that this is an FBX. I imported it into Blender. And I get this. And Blender has the shape keys. I don't think that this was originally made in Blender, but in any case, Blender has the shape keys that describe the extremities. So for smile left, I can interpolate along this scale. For brows up, left, you can interpolate mouth open and so on. So, and why I mentioned the beard thing, notice here that the beard is a separate mesh, and so it also needs to have blend shapes that describe what happens to the beard when the face moves. So when he smiles, like when he smiles right, when the right part of his lips move up, the beard should move up and so on. So that's why this is important. And yeah, there are tons of extremities. If you want to dig deeper, let's see. There's his tongue. He has even tongue motions. So yeah, Blender already has this support, so you're free to play around with this if you're interested. I think that's all I had for this demo for now. Another application of blend shapes nowadays is blinking. So if you want to describe more detailed eye blinks, you would want to use blend shapes for that, because there are deformities that happen when you blink. So I believe he has blinking. We'll see skeletons in a bit, but you can also do it with skeletons. But for more detailed characters, there would be like wrinkles and stuff when you blink. So only blend shapes can describe that well, without having to save every frame. So anyway, let's move on. You can define blend shapes for intermediate steps because, as we'll see soon, blend shapes can only describe linear animations. Eye tracking itself, the blend shapes are only used for the blinking part. The eye tracking itself is typically done with the skeleton, which we'll see soon. To show you an example of somebody creating Blendshapes for the eyes. They have this character, and they're defining blinking as these vertices moving. They messed it up really badly at first, but they're getting there, and so this will be the blink animation. And imagine if you had a really detailed character like in a movie, and they had wrinkles up here, you would need the blend shape to describe those without some kind of physical simulation. So I think he interpolated. So he moves between these and interpolates and stuff. Here we go, this is what I was looking for. So just more detailed blinking. God, this is so annoying. Nowadays, as people get more interested in emotions being represented in games to make more accurate facial expressions, we use blend shapes to describe the emotions, because typically we think of the primary emotions as extremities of facial expressions, and there is this cool example that you can check out, but this guy was he had some kind of project where he was representing these in, I believe, a game. But in any case, you have primary emotions, and you can blend between them to get to the extremity, and you can merge multiple interpolations of these primary emotions to create like intermediate emotions, like over here. I never read this book, but this is where the images came from. If anybody's interested in animation, I suppose you could read this. For real-time performance, especially if you're going to track a real face in real time, like in VR or AR, I briefly touched on this before, but you can use machine learning to learn the blend weights. So if you learn some facial expressions, a machine learning algorithm can figure out what the weights should be to achieve a certain pose from an image or something. So there's this cool paper that came out in 2016 where they were using cameras taped to an Oculus, I think, or some VR headset, and they were using it to do real-time facial expressions. So they used some kind of machine learning network to learn the blend weights, and then they applied them to this character. So I think they learned just the mouth itself. I don't know if they learned blinking or not. I think they did. But blinking is a lot simpler than the lips, because blinking can be described with a single blend shape usually. But anyway, you can see that their results are actually pretty good. And as we get VR headsets that have cameras built into the inside of the headset or near the lens, Rachel recommends the Scott McCloud book that I just mentioned. I forgot what I was saying. Yeah, whatever, it doesn't matter. As we get VR headsets that have cameras built into the part where the lens is, it becomes more and more feasible to do this without jerry-rigging a bunch of cameras to the outside. So that's the point I was trying to make. Like the Magic Leap, for example, has a built-in eye tracker. I don't know if you can get the infrared sensor image directly. Maybe Nolan or Brian might know that, but in any case, as we add more cameras to headsets, it becomes more and more feasible to make these really detailed animations, and we want to do it in real time, so we need to learn the blend weight somehow, because real-time reconstruction, as we'll talk about in the AR chapters, is really, really hard. So some pros of blend shapes: we can represent pretty much any animation step, so a single step of the animation with some linear movement of vertices. This is pretty efficient because you can save essentially a matrix of transforms. You only need really the mesh and delta locations for each vertex that is being used for this blend shape. For facial animation and all of the different types of facial animation like blinking, mouth movements, emotions, we get arguably the best results. And this is something that's hard to justify unless you've used these methods before, but I think a lot of people would agree that This is one of the easier way to make facial animations, and a lot of machine learning and computer vision algorithms try really hard to do it the blend shape way, because skeletal animation, as we'll see, is not as good at these kinds of things. Blend shapes themselves, the extremities, typically represent more natural poses, which means that a lot of the time, an interpolation towards that natural pose is also a natural pose. So blend shapes can naturally represent these kinds of things. Blend shapes excel in situations where the animation sequence is not known, but you do know the range of possible motions. So like I mentioned, voice chat, you don't know what somebody will say, but you know what syllables look like. So if you use NLP, you can figure out, how do I get from some audio sequence to the words, to the syllables, to the blend shapes, and so on. Also, we can use blend shapes to describe really detailed animations, just like geometry caches, such as in movies, or those examples that I showed you before that were in Unreal. Some cons, it can be really, really hard to actually make the blend shapes. We didn't get into AR yet, but normally we use trackers and reconstruction methods, which are, they're not trivial and they're really highly mathematical and they can be hard to implement. There's sort of inconsistent support for blend shapes in general. Nowadays it's becoming better and better, but a few years ago, like maybe 3 or so years ago, blend shapes were hardly supported outside of really high-end 3D modeling programs. You can only represent linear motions. I don't have a particularly good example of this right now, but you can't really represent rotations along a certain axis. Like, it wouldn't be very easy to blend. I don't have the recent. Oh, here's the recent animation. It wouldn't be very easy to blend. If I wanted to. Let me rig it quickly. We didn't get into skeletal animation, but in any case, blend shapes can't easily describe a transformation like this, where you're rotating a bunch of vertices around an axis, and they need to move in a curve like this. Blend shapes can only do linear transformations, like in terms of delta locations. For really highly detailed meshes, they can have pretty bad performance because you need to store, you pretty much need to store the delta location for every single vertex on the mesh in most cases. Another major limitation for really, really detailed applications is that the order of vertices in the actual OBJ or FBX file and the number of vertices needs to be the same, which is often not the case in reconstruction. We haven't talked about reconstruction, so I know it's hard to imagine, but when we reconstruct a room or something like that, or if we reconstruct a person with like a Kinect, we can't usually guarantee the vertex order, so with purely reconstruction-based methods, we can't actually, we can't track which vertex is which easily. Also, blend shapes they might not perform well, or they might just be straight up overkill for a lot of less detailed animations, which we'll see in a second. So, moving on, we finally get to skeletal animation, which addresses a lot of the limitations of other methods that we've seen. The general idea is you create some skeleton, aka an armature, aka a rig, that represents a person's bones, like this. You position the bones of the initial rig so that they're inside of the mesh for some reference pose. Usually people use T-pose because it's simpler. I don't think I have an example of T-pose. T-pose, open recent, Malcolm rigged. Yeah, this is T-pose. I think a lot of people know T-pose because it's a meme at this point. But this is T-pose, and you try to put the rig such that it's inside of this pose. Then you define how much a bone will affect the vertices of the mesh. So we call these weights, and the entire process is called skinning the mesh. So for example, the vertices of your shoulder would deform due to both head and shoulder motion. So I guess I'll show this example again. if this person, if I move up to this person, if I move their neck, you know, let's say that they look left, and I move their shoulder, these shoulder vertices are described by both of those motions. So it's similar to how you interpolate with multiple blend shapes. So after this, you can define animations as a transform of the bones themselves. And like blend shapes, you can describe animations as a bunch of weights plus delta transforms. Except with skeletal animation, you don't need as many delta transforms because you only need to transform the bones themselves. If you were to do a skeletal transformation like this, and then bake the actual positions of these vertices at each frame, you could essentially achieve the same effect as a geometry cache or a blend shape. And as we'll see, we often use the methods in unison nowadays for more detailed animations. Skeletons themselves are usually described as trees. So a bone has a head and a tail, and I believe the head itself is where you would rotate around. Yeah, like if you, let's go back to my animation here, or my example here. This is the head where his clavicle is, or I guess, I don't know what you would call that. Let's say I use the neck bone instead. The head of this bone is at the neck, so when I do some kind of rotation, it will rotate around the neck, if that makes sense. For game engines, game engines will typically expect a single root. In fact, you'll probably get, when you're importing an FBX, some complaint from the game engine if you try to import a skeleton that has more than one root. Typically, this will be some bone that's near the abdomen. So we'll talk about Mixamo, but the hip is a pretty common reference point. And typically, we'll use some tree structure like this. So this is a character in Unreal, and their bone structure is parented like such. You start out from the hips, which will be the root. Then one of the children will be all the spine bones, so it'll propagate up here. You'll eventually get to the neck and the head. And then you'll have another child that describes each of the shoulders, and then it'll propagate this way, and then it'll propagate this way. So you just have to think of the person as a tree. Another child of the hips or root are the legs themselves. So near the hip area, you have a pivot for the left leg and the right leg, and then you propagate the bones down to the toes. And also for the hands, I'll show you an example in a second, but when you propagate from the shoulder joint, for example, towards the fingers, you can describe the entire arm, some of the hand bones, and then the individual fingertips. So I have this example from Mixamo. Again, I'll explain Mixamo in a second, but Mixamo has a structure like this. The structure is pretty much exactly as I said. So, you have hips, spine, legs. And if I move the shoulder, it will move all the children of the shoulder. If I move, if I move a parent, all the children will move with the parent. The same as when you parent game objects or actors. And, it'll keep propagating. So I can move individual fingers like this, and the fingertip, things like that. Same is true for the legs. You can represent the toes the same way as the fingers, but since if you think about it, you don't really see a character's toes that often in a game. But in any case, if I move the leg pivots, it will rotate the leg and so on. So there's my example, and this, like I said, this works the same way as when you parent game objects and actors. So the child will follow the parent, so the finger bones will follow the parent's hand bone, but not the opposite way around. So if I move the head, it won't move any other part of the body. It will only move the vertices that are described as being highly weighted by, or it will only move things that have some weight as described by the head. So any of the vertices that the head will manipulate will move, nothing else will. And if you were to move the root, it would move the entire body. So I'll show you a demo in a second if we have time, but typically we only use local delta rotations because a bone's joint doesn't typically change. Like for example, the upper and lower leg are always joined by the knee. The thing that joins them, like the knee, will never split in half and then move. It won't, like the actual joint position will never diverge unless you get into some horrible accident. So we typically don't need to describe that. As we'll see in a second, if you try to translate a bone, it will cause really horrible mesh distortions. And for humans, if you think about how your joints work in your body, you know, everything is essentially a rotation anyway. You can describe almost any human animation, at least for the body itself, as a rotation around the pivot, like a bone joint. And the reason I mentioned local specifically is because your skeleton can be oriented in any way in the game world, but you still want, you know, if I want to move my arm up, I shouldn't have to worry about how my character is positioned in the game. And, you know, we'll talk about this in a second, but you can limit how much the bones will rotate by applying kinematic constraints. I'll show you an example of when you don't limit it. So it's demo time. Let me create a Blender instance. Actually, let me do a couple of things first. Before I show you how to rig something, I'll show you the example of what happens when you try to do things like translate bones. So, like I was showing before, say that I want to move this guy's leg forward like this. You know, this is a rotation around the x-axis in this case. Like if I want him to kick something. It would be really, really bad if I tried to do a translation like this because of the way that the weighting works. You just never really want to translate bones. It doesn't make sense, and the result is pretty much always horrible. Like, if I want this guy's arm to move in front of him, I wouldn't translate this bone forward like this. Instead, I would just rotate around the z-axis. So, almost all human animations that we care about can be described as bone rotations. Also, to extend something that I talked about before, if you want to do blinking where you're not as worried about the deformation, you can do it this way. Oh wait, this is the eye, never mind. I guess Mixamo does have Blendshapes for... Yeah, sorry, I'm using the Mixamo mesh. Mixamo has Blendshapes for the actual blinking. I might have to show an example next time of how you can do blinking with skeletons. But anyway, this is an eye rotation. Anyway, to show you an example of how to rig something, let's say that I want to rig a cylinder like this. I'll make it a long cylinder. Let's say that this is somebody's arm. I'm going to use the remesh modifier in Blender, which it'll essentially it'll uniformly divide the mesh into like rectangles so that you don't have these super long faces, because that will break things. Anyway, I'm going to rig this, so I will add, Shift A, I will add a bone, and Blender has this X-ray function so you can see the bone. I'm going to add a bone, and I'm going to start here. Let's say that I want to describe this thing with like 3 bones, so make another bone here, another bone, whoops, another bone here. So these are some joint positions that I can use to manipulate the cylinder. I can, in Blender, you rig something by trying to parent it to an armature. So I set the parent to this armature, and I ask Blender to make the weights for me. And Blender did make the weights for me, so you can go to weight mode and see that it made weights for me. Anyway, so in pose mode in Blender, you can move parts of the armature. So the head of this bone is the root of everything. So if I were to rotate this, it would rotate the entire mesh. If I rotate it at this joint position, it will rotate it around this pivot point because this is the head. If I rotate it up here, it will rotate around this pivot point. So that's my very simple demo of animation. And for humans, it's pretty much the same except more complicated. And you can also, kind of like how with Blendshapes, you would have to describe Blendshapes for like facial hair and stuff like that. You also need to define weights for any kind of accessories like shirts. So the shirt in this case is a separate mesh, so it also needs its own weighting. It needs its own weights relative to each bone and so on. So I think that's it for now. We don't have enough time to talk about the rest of skeletal animation, so you're free to leave. If anybody has questions, you can ask them. Otherwise, I'll just stop my recording. Alright, well, bye.